Okay, fun fact. I recorded this whole video and then my computer was so overwhelmed emotionally, apparently, it just stopped recording my screen and just recorded my voice. So I have like 30 minutes of me explaining this with no text. Okay, so I'm gonna try this again and see if we can do slightly better this time. Okay, so this here at the beginning is basically just talking about the idea that we're going to have some notation changes. One of them, or the two big changes, are that essentially we're going to, instead of calling like TF being the final time, we're just going to say just T by itself is always considered the final time. X by itself is always the final position. V by itself is always the final velocity. Along those lines, the initial is always called V sub zero, and the way we pronounce that is not. So you need your like Downton Abbey voice, not. Come on, pen, not. NAUGHT. So like there is not to worry about here, kind of thing. So delta V would be V minus V naught. Delta X is X minus X naught. Um, and the only real change or difference is T. Delta T is just T because we assume T naught is zero. So we're assuming we're always starting at time equals zero. These are actually pretty big assumptions that all go away eventually, depending on how far into physics and life you get, or engineering. But for the purposes of today, we can just say not, and we're good. Okay, now another big assumption that we're going to take is that acceleration is constant. That means it does not change with respect to time. So in calculus, the way that we would write that is d acceleration dt, come on girl, d acceleration dt is equal to 0. Okay, got it? All right. Now, your book explains this a really weird way without using calculus, which I don't understand because calculus makes a lot more sense than whatever it is they're trying to do. So I'm going to teach this using calculus, and if you don't like it, that's what the book's for. Okay, so let's say that we have acceleration that we have defined as the derivative of velocity with respect to time. Good, good, good. Okay, so without too much problem, are you cool if I just put the dt over here? It's like kind of like you multiply both sides by dt, except that's not really what you do, but you know, we're not mathematicians, we're physicists-ish, and so it's fine, I guess. I don't know. All right, so we're moving the dt over, and then we're going to integrate, and we're going from t naught, which is 0, to some generic t, and some initial v naught to some generic v. Okay, so this over here on the right might give you a little bit of pause if you remember integration. So if I have, come on, pen, you got to be with me. We're not going to do this. And there's cuckoo clocks going to talk about it to you. Okay, come here. All right, so if I had like t, come on, girl, squared plus 1 dt, you know, from whatever to whatever, it would be like 1/3, whoa, 1/3 t cubed plus t, and you would evaluate it at the limits, you know, 1 to 5, or you know, whatever it happened to be. Man, pen, we need to have a long talk. Okay, so something like that, except with real numbers. Okay, so if we just had the 1 by itself, like 1 dt, it would just go, you know, and from 1 to 5. That's supposed to be a 5. Then it would just be t, right? Evaluated from 5 to 1. Okay. Now another way we could also write that is just saying integral dt, because the 1 is implied. And if the 1 is implied, then we just have t going from 1 to 5. Okay, so kind of along those same lines over here for a is constant. So since a is constant with respect to time, we can pull that out. And so now we just have like kind of 1 dt equals an integral 1 dv. So we can just evaluate t and v at those limits. So we've got that, and then without too much trouble, we can keep going. Get a times t minus 0 is equal to v minus v naught, and then if we solve for v, we get v equals a times t plus v naught, okay? So this is our first really important equation that we want to start with, that basically just says the velocity is the initial acceleration times how long we were at that acceleration, plus the initial velocity. Now again, this only works because we assume time equals 0 at 0, and we've timed at the beginning, and we've assumed acceleration is constant. But just so that you kind of know that this makes sense, so velocity is in meters per second, and acceleration is in meters per second squared, time is in seconds, velocity is in meters per second. So, this and this will cancel out. So you got meters per second equals meters per second plus meters per second. So the units cancel, or the units not cancel, the units make sense. So that's a pretty good indication that we're going the right direction. So I'm not entirely sure. I mean, I think your book is just trying to avoid calculus. But you guys, y'all are grown-ups. This is a Cal-based physics class. You can handle it. So this is where this initial equation comes from. This. To-do. Okay. All right. So the next thing that we're going to look at is actually taking this to the next step. So say we've got, so we know that velocity, okay, we have velocity with respect to acceleration, but we also know velocity with respect to position. It's dx dt, right? Okay, perfect. Ba-doop, ba-doop, ba-doop. Oops. So we know the velocity is at plus v naught. So we have well, hold on. I guess I could go ahead and I could do v dt equals dx, just like that. Okay, but I know that v is at plus v naught dt equals dx. And then I integrate from x naught to x and 0 to t. And because I'm kind of super awesome at all things, nothing really, I feel like I've recorded this video 100 times now because my computer isn't functioning the way I want it to. And evaluate all of this from t to 0, and then x evaluated from x to x naught. And then that gives me 1/2 a, I'm also hitting buttons on the side of my pen, which doesn't help, at squared plus v naught t equals x minus x naught. So x equals 1/2 a t squared plus v naught t plus x naught. This is the other super big important equation that you're going to want to have. Okay, now look at the dimensions. Acceleration is meters per, meters per second squared times second squared, then plus meters per second times seconds plus meters, and shockingly, that gives us meters plus meters plus meters, which is in fact meters. Yay! And that's what we want. Okay. So these two equations here are really important. They are super related. They're everything you ever wanted in an equation, but they are only valid if acceleration is constant and assuming the initial time is measured from time equals to 0. So if it's like, if time starts at 3 seconds, if movement starts at 3 seconds, then you have to just deal with other problems. But hopefully I don't think that happens in this class, so we should be good. Okay, so here's this wonderful equation. All right, now there's a second or an extra bonus equation that I definitely never remember learning, although I think in theory you might have, or I think I might have learned it and just not remembered learning it. So remember we have velocity, dv dt equals acceleration, and we have v equals dx dt. So one of my favorite things to do in math is divide equations by each other. because then you can get stuff like this. So acceleration over velocity equals, come here, equals girl, equals girl. Ah! Yeah, apparently my computer just can't handle recording anymore. Equals dv dt over dx dt, like that. Make sense? Okay, so I have a over v equals dv dt, and since I'm dividing by dx dt, I can also multiply by the reciprocal dt dx. And look, my dt's cancel out. We're pretending that's a thing that we can do, and you can do it, and it's fine for the purposes of not being like a hardcore mathematician. Oh man. All right, now we're gonna cross multiply, which is another thing that kind of gives me heartburn, but again, we're just doing stuff. All right, so then we get a dx equals v dv. Okay, integrate from some x naught to some x final, from some initial v to some v final. Acceleration is still constant, so that comes out, and we have a times x from x to x naught. Now v is not constant with respect to v, so this is just like x dx, so it's 1/2 v squared evaluated from v to v naught. Okay, so a times x minus x naught equals, I'm going to go ahead and put the 2 over there, v squared. So v squared minus v naught squared. And now I play around and I get v squared equals 2a x minus x naught plus v naught squared. And you're like, that's wonderful, and I don't care. And you would not be entirely wrong for feeling that way. Okay, but what's cool about this is if you ever remember this equation exists, you can use it, because notice a variable it does not have in it, and that's time. So most variables, or most of these equations so far have all had it with respect to time. This one bypasses time, so if for some reason you're given positions and accelerations and velocities but not time, I always remember in physics having to like calculate time and then like use the equations twice. So rather than using equations twice, you can just go straight to this one. Also, if we're gonna dimensionally analyze this, we can do that. So we have meters per second, come here, squared, and that's equal to 2, which has got no dimensions. Come on, computer, I just need you to keep up for the purposes of making this video, equals 2 times a, which is in meters per second squared, and then meters minus meters is still meters, and then plus meters per second squared, meters per second. Come here, girl. I'm gonna write real slow so you can keep up. And meow, 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 meow. Okay, so there we go. That's a terrible 2, but you know, we're doing our best. So as you can see, on the left we have meters per second, meter squared per second squared. On the right we have meter squared per second squared plus meters squared per second squared, even though you can't actually see it. There we go. So all the dimensions work out. So your book goes through all these different ways of explaining things without using calculus to get to the same answers that I just got to. But I think that y'all are big, giant, grown-up people who can understand and process calculus. I'm going to work these examples separately, just to kind of work through them with you. But 100%, I think you can process those without doing that. So here are the equations we want you to learn. The other things that talk about average velocity is starting velocity, and the other velocity divided by, yeah, I get it. But I think what's really going to be powerful is what I have for there calculated for you in blue are those. And a lot of times you can get away with just the first 2. The second one is like honors equation, that if you can remember that one, then you're in extra good help.